there anybody who did not understand what to do on this?
No, it's pretty easy.
All right, anybody just want to explain it just for general principles? Gracie, you want to explain it?
Well, I know what to do.
All right. Give me a second. Let me get closer to you. As I walk quick.
So you're kind of like plugging it in because it's giving you like the different ways.
Okay, so what do you mean?
So it's like for the squares, it's just kind of giving you like if it was a square root, it would have been what it would have been like or looked like.
Okay.
And then the square roots is at the other side because it's giving you another example. And then the process, it's showing you the process, so you're breaking it down so that later on you'll be able to look back in the notes and see it.
So something like this. 5, 5, 25, etc.
Yep.
All right, is there any questions on that? All right, we are moving on. Yes, so we are covering 4 pages today, and we're doing some story time.
Oh, that's good.
And I literally do mean story time. Okay, so go ahead and flip over to page 70. I want to walk y'all through this one real quick. Page 70. So, page 70. If you notice, I want to draw your attention to a couple things. One of which is this is a supporting standard. You don't have to highlight anything. I'm just drawing your attention to it. That way you know. All right, so our verb here is to use, and we are going to use models and diagrams to explain the Pythagorean theorem. Gotta love stuff and things. All right, so we're going to have models, diagrams, and of course the Pythagorean theorem. Yes, I know that's a really big word, Pythagorean. It's basically because of this dude named Pythagoras, like 3000 BC. Most of the math you guys use today was all in like 1,000 to 2,000, even 3,000 years before our time as we know it started right now. All right. There's a couple of vocabulary words you got to know.
Which page is this?
69. One of which is adjacent. Adjacent just means it's right next to each other. All right. Converse. Basically, you're just trying to figure out if this is a right triangle. So you have A, B, and C. So basically, A plus B is, and that's A squared plus B squared equals C squared. Sorry, the little squares look weird. But those are A squared plus B squared equals C squared. Hypotenuse. Does anybody remember what a hypotenuse is? Okay. Draw yourself a picture. I'm going to do mine in a different color. That way you know that yes, what this is. So we're going to draw a right triangle. Right triangle, remember, is named for the right angle. I want you to go ahead and color in that right angle. Because directly across from the right angle is your hypotenuse. This is also what we call C. C. Hypotenuse for us is always called C. Legs. Go ahead and draw another right triangle. Go ahead and fill in your nice little angle. These are what we call the legs. We use this as A and B. Now, which one you put A and B on, it does not really matter. And we're going to go ahead and rewrite the Pythagorean theorem. So A squared plus B squared equals C squared. All right, is there any questions? And basically when it's doing a square, it's just saying 3 squared is equal to 3 times 3, which would equal 9. And then this would be the square root of 9, which is equal to 3, because 3 times 3 is 9. All right, theorems. You'll hear a lot more about this when you get into geometry in a couple years. Theorems are basically a statement that somebody came up with a very long time ago and figured out this is always true. And since it's always true, they call it a theorem. Just like our exterior angle theorem, where the 2 inside angles equal the one on the outside, as long as they don't touch it. Y'all good with that? All right, any questions on any of this vocabulary? Okay. All right, so I told you story time. But this also means you're going to have to be a very nice audience. That means you cannot do a whole lot of extra talking today. Make sense so far? So it says, what's your angle, Pythagoras? And this is Pythagoras. Gentlemen, do I need to split y'all apart? Okay. All right, so you got Pythagoras. This is actually a fictional story based on a real person. So one day, Pythagoras sat in the shade of an old olive tree. He could see the harbor and the sparkling blue sea around the island where he lived. Nearby, 2 workmen were building a temple. They began to argue. "This ladder is too short to reach the roof," Pepros grumbled. "That's not possible," said Saltos. "The wall is 12 feet tall, so I made the ladder 12 feet long," Pepros roared. "The ladder only reaches the roof when it is flat against the wall, and then no one can climb it. This is as bad as the columns on the porch." Pythagoras poked his head out from behind the tree. "What's wrong with the columns?" he asked. Pepros frowned. "It's that pesky Pythagoras again. Stop bothering us. At this rate, we'll never finish the temple." As the workmen argued, Pythagoras crept around to the other side of the building. 4 columns stood on crooked bases. Some columns leaned to the left, others tilted to the right. "These columns will never hold up a roof," Pythagoras said to himself. "I wish there was something I could do to help." Still thinking about the problem, he ran home for dinner. What do y'all think about those columns? Do you think they're going to be good enough for anything? Yeah, probably not. When he got home, his father was talking about his ship. "I sailed to Crete with a shipload of tiles, but Lepus and Boundus got there before me. With their fast new ship, they will take away all my customers." Through a mouthful of bread and olives, Pythagoras asked, "Father, you always sail to Rhodes first and then to Crete. Why don't you just sail straight from here to Crete? It would be a lot faster." "It's too dangerous," his father replied. "It would not be safe to sail straight from here to Crete unless I knew the exact distance. Out at sea, I could miss Crete and end up anywhere. I'm leaving for Egypt tomorrow. I want you to come with me, son. One day you will command my merchant ships, and you have much to learn." At dawn the next morning, Pythagoras and his father set sail. As they sailed along the coast, Pythagoras said, "I can't wait to see Alexandria. I hear they have great buildings there. I might want to be a builder someday." "But son, you're going to be a merchant," his father said. "The life of a merchant is exciting. You get to sail away to faraway places." He put an arm around Pythagoras' shoulders. "You just have to look at it from the right angle." Soon they were sailing into the port of Alexandria, the capital of Egypt. Pythagoras marveled at the great lighthouse that stood proudly against the sky. "Saltos and Pepros should see this," he exclaimed. At the dock, a man greeted them. "I am the builder, and I'm going to let y'all try this one. You ready?" Anybody want to try that one? Landon, you want to try? No? But people call me Neff. And so,
you try to do it.
oh boy. It says, at the dock, a man greeted them. I am the builder, Nefer Hepper Hersifkaper. There you go. You're welcome. Now y'all can laugh.
The words are silent.
Yeah, no idea. But people call me Neff. I'm here for the tiles. Pythagoras was excited to meet a real builder. Have you built anything around here? He asked. Neff nodded. As a matter of fact, I helped to build the lighthouse. How did you get the base so straight? Pythagoras asked, thinking of the crooked columns back at home. You must be a master builder. Neff smiled and stuck out his chest. The secret is this special rope that's been used by my family for ages. You use a knotted rope to cut stone, Pythagoras asked. Neff laughed. My dear boy, this rope does not cut stone. I use the rope to make a special triangle. I call it the right triangle because it helps me make a nice square corner that's exactly the right angle for cutting stone. Neff let Pythagoras hold the rope. Pythagoras made some triangles, but none had the right angle. How long do you make each side? He asked. Oh, I've shown you too much already, chuckled Neff as he took back his rope. Why don't you run along now? As his father and Neff talked, Pythagoras found an old piece of rope and tied knots in it. He pulled the rope into different triangles. Finally, he made a triangle that seemed right. It had 3 lengths on one side, 4 lengths on another side, and 5 lengths on the longest side. I've got it, he said to himself. So you see what he's doing there? Just then, Pythagoras' father called him. Carry this crate of tiles, son. Neff and I will carry the rest. I would carry them, Neff sighed, but I've hurt my thumb, so I can't. You'll have to make 2 trips. Can y'all imagine a hurt thumb causing somebody not to be able to carry something? I'm seeing some head shakes there. When they got to the house Neff was building, he said, While you get the rest of the tiles, I'll get the money I owe you. Grumbling, Pythagoras' father headed back to the ship. Neff patted Pythagoras on the head. Be a good boy and watch these tiles for me, he said as he disappeared in the house. And don't touch anything. What do y'all think? Do you think he's going to touch stuff? Yeah. Pythagoras looked around the sunny courtyard. In the middle stood a statue base made of stone. He took some tiles out of the crate just to see how they would look around the base. I can put them back quickly, he thought. He made a row of 3 red tiles along one side of the statue base. He added 2 more rows of red tiles, making a square. Some of these crates have blue tiles, Pythagoras said. Soon, red and blue tiles were scattered everywhere. Pythagoras made a square of blue tiles and a big square of red and blue tiles. He was admiring his work when he noticed. This statue base is a right triangle. Its sides are 3, 4, and 5 tiles long. Strange. He counted the tiles. Strange, he thought. The 9 tiles in the red square plus the 16 tiles in the blue square equal 25 tiles. There are exactly 25 tiles in the big red and blue square. Suddenly a voice demanded, What do you think you're doing? So do y'all see what he did there? His 2 together made the big one. Neff rushed into the courtyard. Pythagoras' father was right behind him. What's all this? Neff snapped. I'm sorry, Pythagoras said. I was going to put the tiles back, but I found out something interesting. I don't care what you found, interrupted Neff. Look at this mess. Pythagoras, pick up the tiles, his father said sternly, and hurry. We have many more stops to make today. The next day, Pythagoras and his father set sail for home. To pass the time, Pythagoras drew a picture of the tile squares he had made. The square with 3 tiles on each side had 9 tiles, and the one with 4 on each side had 16 tiles. The one with 5 on each side had 25 tiles. So on a square, the length of a side times itself is the number of tiles in the whole square. I'll call it squaring when I multiply a number by itself. 3 times 3 is 3 squared. I'll write it as 3 to the power of 2. Hey, isn't this the same thing we were doing for warm-up today?
Yes,
Maybe there's a reason. Pythagoras drew a new picture. 3 squared plus 4 squared equals 5 squared, he said to himself. I wonder if the squares on the sides of other right triangles add up the same way, he thought. What do y'all think? Do you think they add up the same way? Pythagoras practically flew off the ship when he got home. He couldn't wait to tell Saltos and Pepros about the special knotted rope and the secret about the right triangle. When he got to the finished temple, Saltos and Pepros were not there. The ladder was on the ground where Pepros had thrown it. That ladder would be easy to climb if the bottom were about 5 feet from the wall. Pepros said that the wall is 12 feet high. He drew a triangle in the dirt and wrote 5 squared plus 12 squared equals question mark. So 25 plus 144 is equal to 169, and 169 is 13 times 13. That's it. The ladder needs to be 13 feet long. He fixed the ladder and headed home. At home, Pythagoras got out a map. He looked at it closely. I wonder, he said to himself. That night, Pythagoras announced, I found out the distance from here to Crete. His father nearly choked on a fig. His mother asked, How can that be, son? Pythagoras answered, I discovered a pattern that works for any right triangle. I used it to figure out the distance. Now father can sail straight from here to Crete. His father stood up. Son, I cannot risk my ship because of some triangle. What do y'all think? Do you think that's a smart idea? You think he shouldn't risk his ship, or do you think he should trust Pythagoras? Father, Pythagoras started to explain. At that moment, Saltos and Pepros came rushing in, puffing hard as they had raced up the hill. Pepros turned to Pythagoras. You did something to our ladder. Has Pythagoras been bothering you again? His father asked, frowning. Saltos shook his head. No, he made our ladder the perfect length. Now we will be able to finish the roof now. Pepros added, then all we'll have to do is fix the crooked bases of the columns. Maybe I can help, Pythagoras offered. Use my rope to make right angles. If you use the right angle to make the bases straight, the columns will stand straight. Saltos laughed. Great. Now we can finish the temple on time. You're welcome to stop by and help us anytime you like. Pythagoras' father said, Son, on second thought, maybe you should tell me about the distance to Crete. Pythagoras explained. Our island, Samos, forms a right triangle with roads in Crete. If I call the sides of the triangle A, B, and C, I can use my right triangle pattern, A squared plus B squared is equal to C squared, to figure out the distance from here to Crete. Now, if y'all remember correctly, on page 69, we also had an A squared plus B squared equals C squared. You can see how A squared plus B squared equals 34,225. To find C, the distance between here and Crete, I had to find what number multiplied by itself equals 34,225. I knew 148 to the power of 2 equals 21,904. That's too small. I tried 200, but 200 squared equals 40,000. That's too big. I tried 180, and 180 squared equals 32,400. That's close. And then I tried 185 times 185. That's exactly 34,225. So the distance from our island to Crete is 185 miles. Y'all see his mouth there? Everyone was amazed. Pythagoras' father clapped him on the back. Good thinking, son. You'll make a fine merchant someday. Pythagoras' mother said gently, perhaps he can use his quick mind for other things. His father nodded. Son, with your clear thinking, you could be a general, a senator, a teacher, or anything you want. It's your choice. Pythagoras smiled. He hoped to do great things in the future. A few days later, Pythagoras saw his father's boat, sailing into the harbor. His father ran to greet him. Pythagoras, you were right. I made it to Crete in record time, his father said, hugging him. Pythagoras looked up at his father and said, you were right too. I just had to learn how to look at things from the right angle. All right, historical note. Pythagoras was born on the Greek island of Samos around 569 BCE. The actual events of his childhood are unknown. He founded a school in southern Italy after traveling in Egypt and the Middle East. He was a philosopher, musician, and astronomer. But he is most remembered as a mathematician. His most famous discovery is what we now call the Pythagorean theorem. When A and B are two legs of a right triangle and C is the opposite of the right triangle. So what y'all think? Did y'all like that? Yeah. Alrighty. So, go ahead and flip over to page 73. We're going to do something very similar to what Pythagoras did in our story. So what do y'all think we're going to start with? A triangle. What kind of triangle?
Right.
It's got to be a right triangle. This theorem will not work with any other triangle. So I'm going to fill in my little right triangle here. And we're going to call this 3, 4, and 5. Anybody have any ideas what I'm doing here?
Nope. Making the squares.
I am. That one's not quite right. So I'm going to do 3 there. 3 there. How y'all doing so far? I take it some people have already gotten their third square. I'm going to stay on the way. Let's see. Now, granted, my squares may not be perfect, but y'all get the idea. Hello. 1, 2, 3, 4. And then 1. It'd be good if I could have my nice little stuff straight. 1, 2, 3, 4. All right, now my nice little numbering is going to be a little different here. 3, 4, 5, 6, 7, 8, 9. And then I'm going to restart and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Alrighty. So, and I'll go ahead and highlight mine that way y'all can see some stuff here. Oop. Probably don't want the whole thing, do I? No. Back to here. There we go. 9. And then, if you notice, the rest would have been blue. Sorry about my bad coloring. Alright guys, so basically Pythagoras said any right triangle, if we square the two smaller sides, it'll end up being the same size as the larger triangle. The most famous of our triangles is called the 3, 4, 5. That means I could do 3 times 3, I could dilate this. That means make it bigger or smaller. So this time I'll make it bigger. If I was to multiply all these numbers by 3, I could say that 9 squared plus 12 squared equals 15 squared. So y'all are going to check this in your calculator. What is 9 squared? What is 12 squared? And what is 15 squared? 225. Does 81 plus 144 equal 225? That means this right here is a right triangle. Now, how did I get those numbers? I multiplied 3 times 3, 4 times 3, and 5 times 3. What if I came up with a different triangle? What do y'all think of some numbers? We're going to find out if some stuff's a right triangle or not. So somebody give me a number.
6.
So 6 squared plus
4.
4 squared. And what do y'all think? 10. So we're going to check this. We're looking to see, is this a right triangle? And we're going to put a question mark. So what is 6 squared?
36.
What is 4 squared?
16.
16? And what's 10 squared?
100.
Does 36 plus 16 equal 100? No. So this does not equal. This is how you could tell if something's a right triangle. That means if we were to try to draw this as a triangle, it wouldn't work. I mean, we may try to make it work, but as you can see, mathematically, it does not. All right, is there any questions on any of this? What you got?
Because it doesn't equal 100, does that mean that the 6, like the square would have to equal 100 for it to be right? They both have to equal it?
Yes, they both together have to equal 100. So let's go ahead and change these up just a little bit. So let's say,
I thought it would still be 100 because it's the same thing.
well, what is 36 plus 16?
Not 100.
If I remember correctly, it's 52.
I thought it was,
Yeah.
yeah.
Does 52 equal 100?
No.
No. And that's the reason why we can say no, it does not.
So it has to equal 100?
It has to equal 100.
Okay.
Now, we could figure out something that does. We could say, okay, and we could go, Let's say we wanted to keep our 36.
If it was over 100, would it still be a right triangle?
Well, let's find out what it would be. So this right here is a way we could figure out our missing side. So we'd have 36, and actually I'm going to change this to 10 squared. My bad. I'm trying to get ahead of myself. So let's say this becomes 36 plus b squared is equal to 100. Now I could subtract this because guess what? All these are, it's just another equation. So what's 100 minus 36? Now, this tells me what b squared is. If I want to know just b, I would take the square root of both sides. So what is the square root of 64? That means if I was to do 6 squared plus 8 squared is equal to 10 squared, that would work.
So this one would be a right triangle.
Yes, ma'am. This one would be.
So with the one above, it was 225, but it's still a right triangle?
Because 81 plus 144 does equal 225. As long as the two equal the number, because in this one, 36 plus 64 does equal 100.
Yeah.
That's how you know if it's a right triangle. And you'll know if it works with Pythagorean theorem. Because we can use the Pythagorean theorem to figure this out. Any other questions? I will be honest with you guys, this is the one thing most 8th graders really do like. Mostly because it's all it is calculator play. All right, any questions on this? All righty.